Okay, welcome back to our third and final portion of session 17. In this last portion, we're going to introduce another way to perform the rotations that we've been talking about, these transformations to go from one depicted state of stress to another depiction. Okay. And in this case, we're going to look at using stress tensors, which we've talked about briefly back in session 4. So it's been a little while. But a stress tensor has 6 unique components for our intents and purposes, as we can see here. And a rotation matrix is probably not something you've dealt with a whole lot, but it can be defined as having this type of matrix if you're rotating about the x direction, this matrix if you're rotating about the y direction, and this matrix if you're rotating about the z direction. Okay, so if you haven't done these types of rotations before, it's okay. What we're going to end up doing is essentially using Python to perform these appropriate matrix multiplications, okay, as we see here. So this new tensor, sigma prime, okay, so we're going from the original tensor to the new tensor, right? This is describing a state of 3D stress now, not just 2D stress. Sigma x, tau xy, tau xz, tau yx, right? And these are symmetric in that tau xz, tau zx, tau xy, or this is equal to this one's equal to this one's equal to this one's equal to this, right? So this is kind of the original state. And now what we're saying is that really, if we use tensors, we're not constricted to just doing 2D transformations. We can come up with a new state of stress, okay, for even multiple rotations if we want. Okay, we're not going to go that deep, okay, to go and come up with this new sigma prime tensor, all right? And this is done through multiplying. You could, this is associative, so either way, so you can do sigma times r transpose, and then r times that. You do r times sigma, and then that quantity times r transpose. If you have not done much with matrices, don't worry about it too much, because you're going to have the code. It's already up in a nice Colab file where you can kind of plop these numbers or these values, the appropriate rotations and appropriate values, into the code, and it's going to spit out a new matrix, okay, with the sigma prime tensor. Okay, so a subtle point here is that these rotation matrices are actually the transpose of the rotation matrices posted here. And I mentioned this previously in the first portion, but when we're rotating a vector in a frame, it's one form. It's actually the transpose of these. Okay, if you stay in the same reference frame but you rotate a vector, then you use the transpose of the vectors, the transpose of the rotation matrices shown here. But if you're rotating a reference frame, like it's a body fixed, okay, so there's we're getting to just some jargon, but if you've got, say, your element and you're rotating it, okay, with the reference frame, then it's advisable to use these forms as they're shown here. Okay, let's do an example. We say we have this state of stress, sigma x equals 50 megapascals, sigma y equals 100 megapascals, tau xy equals 0. What are sigma x prime, sigma y prime, and tau x prime, y prime when the angle of counterclockwise rotation theta is 30 degrees. So this is going to be a z rotation, okay, of 30 degrees. So we use the RZ, okay, this is the rotation matrix for RZ, and theta in this case is 30 degrees, and we can plug it in right here. So you can plug in 30 degrees into this, and you get square root of 3 over 2, 1/2 minus 1/2 square root of 3 over 2, okay, and that's your rotation matrix. This is the tensor associated with the initial state of stress. Sigma x is equal to 50, sigma y is equal to 100 megapascals, but tau xy, all the other shear stresses are 0. So the rest of the matrix does not have any terms. It's all zeros. So what do we do with this? Well, we can apply the equation that we have here, where we say it's R times sigma, okay, times R transpose. So that is what's in the code. Okay, if you see here, we define this sigma matrix, right? You can take a look and run it. We define this rotation matrix, RZ, all right, using the terms that we have here, where all these taus are equal to zeros, and this is the theta of rotation, okay, associated with rotation. And we can then perform the matrix multiplication. So in this case, we have dot products. Okay, that's Python. The way, if you use multiply in Python, that is element by element multiplication, we really want to use their dot product function. Okay, so for example, this is saying sigma times, or sigma dotted with the transpose of RZ. Okay, that's what this is, the NP. So this is doing that operation, and this is dotting this with this, and then this is dotting RZ with the result of that intermediate matrix. And so then what we get is this sigma prime. So this is what gets spit out. Sigma was this, okay, it looks a little messy. RZ was this, and sigma prime was this. If you just rewrite things, what you'll see is that sigma x prime is 62.5. Tau x prime, y prime, okay, is 21.65 megapascals, and sigma y prime is this component, 87.5 megapascals. And this is what we got previously when we did the 2D transformation, okay? So this is a nice computational technique that's not too complicated, that can allow us to calculate out the new sigma prime tensor, okay, for the 3D state of stress. So what I'd like you to do, this is the final problem for this session, is to take the state of stress, all right, sigma x equals 50 megapascals, sigma y equals 100 megapascals, tau xy equals 10 megapascals right here. And, you know, before we had to do or restrain our rotations to 2D, right, about the z. What happens if you rotate 90 degrees about the positive x-axis? Now, you can maybe visualize this, okay? That's fine, and that's what we're doing here, okay? We say, okay, look, we've rotated about x 90 degrees. Now we have a new x prime, right? So that this x prime and this x are in the same direction. This was the minus y direction, right, down here. And now when I rotate 90 degrees in the positive x-axis, right, what was z, which was originally coming out, is now facing down into the minus y. So that z prime is like this. Okay, so you can do this by modifying the code in the Colab file if you like. Okay, or you might think about just trying to visualize it, because we're doing a 90-degree rotation, so we know that magnitudes of things are not changing, but it can be a little bit confusing. And so you might take a hypothetical guess in terms of what is the resulting state of stress, okay? How is, for example, this sigma x changing? Is it changing at all? Is it, or what is it? What is sigma x prime? Maybe it's something very similar to what we had here. What is, what's happening with the shear stress? What's happening with the 100 megapascal sigma y, okay? Because the box, they're still acting, but now they're acting on these newly defined faces. All right, well, thank you. I hope that this session has been helpful in understanding how we can perform transformations on elements, mostly, essentially 2D elements mostly, but now we've actually discussed how you can do it with a tensor for 3D elements, and figure out how the normal stresses and how the shear stresses are changing as a function of rotation. Great, thank you. See you next time.